Hello, today I will be talking to you, or teaching you, an equation that I learned by Charles Balin, and he is a person who has an open course at Yale, and he's actually the course is at iTunes U, so I'll be putting that in the description, a link to that. And what he talks about is called the Newtonian. Please excuse my handwriting. Hopefully it'll get better when I do more of these. The Newtonian modification of Kepler's third law. And this equation goes a cubed equals g m p squared over 4 pi squared. Okay, so this is just a collection of letters, unless you know what each of these letters stands for. So A equals the semi-major axis of the planet we're talking about. And so a semi-major axis, here I'll draw a little diagram of this. Say this is a sun, and this is a planet's orbit, and let's call this planet Earth. You may not be able to read that, but okay. So the semi-major axis is the distance from Earth to the sun, or any planet really, to the sun when it's farthest away from the sun. And this is the semi-major axis. The major axis in general is this and this. Usually this should be right in the middle, but you know, not the best drawer in the world. And so this right here, the distance right here, that is A. Now, okay, now let's move to G. G equals what we call the gravitational constant. It is the gravitational constant. And the gravitational constant is just a number that shows how gravity affects other bodies in space. Okay, we'll move to M. M equals the total mass of the orbiting bodies. So the orbiting bodies in this case are the sun and the Earth. And so M is the total mass of the orbiting bodies. Okay, that brings us to P. P is the orbital period of the planet. And so, how long does it take the planet to go around once? And, of course, Earth's orbiting period is 1 year. And then we get to the lower equations. 4 is 4, and pi is approximately 3.14, you know, it goes on. Okay, so we have a collection, instead of a collection of letters in an equation, we have a collection of words. Semi-major axis of the planet cubed equals the gravitational constant times the total mass of the orbiting bodies times the orbiting period of the planet squared times 4 pi squared. That is a squared right there. Whoop. And so that does nothing. That's nothing unless you give these letters measurements. So we're going to give A a measurement So let's do Earth. How about we do that? In order to explain this, I will use Earth as an example. Because it is easy, because astronomers are very egocentric when it comes to their planets. And so we name all of our units of measurement about Earth and the Sun, but really what else do we have to name after? So, do that. Okay, so if we're going to measure this, the semi-major axis, in units, we're going to use it in what's called astronomical units, which is the distance from the semi-major axis of the Earth, which is 1 AU. That's it. Or 93 million miles, according to the They Might Be Giants, and every other science textbook in the world. So we'll do 1 AU cubed equals G, and we'll keep it at that because G's complicated. M for our solar system is called the solar mass, and that's the total mass of the Sun and the Earth, and that's represented by the M for mass, and an O with a little dot in it, and I'm guessing that the dot is the Sun, and the O is the orbiting path of the Earth. And then we have P, which is the orbital period, so we have 1 year. Squared. And then we have all this over 4 pi squared. And so that's a pretty weird equation right there. But don't worry, astronomers do this really, really cool little thing called taking, or how Mr. Balin puts it, taking the general equation and dividing by the specific equation. So do this. I think we should skip. We could take a page now. Okay. So our general equation is a cubed equals GMP squared over 4 pi squared. And we're going to divide that by our specific one, our specific equation. But I'm going to change this because I do not like having fractions when we're going to be dividing. You know, you've been taught this if you've been through middle school, you've been taught that you don't want to divide fractions over another thing. So we don't want to divide this. So I'm not going to multiply to both sides. That would be sort of weird. How about we just write it out differently so it's just a bit easier on the eyes. I mean, we're still dividing fractions, but it will be easy. Just let me show you. We're going to divide it by 4 pi squared. And so you might be saying, yes, that's still a fraction, just set out differently. And you'd be right. But if you watch what I do, it's a lot easier when we divide by the specific formula. So I'm doing this all for a reason. 1 AU equals G solar mass 1 year divided by 4 pi squared. And what do you know? The G's, which is a very long and complicated number, they cancel out. And the 4 pi squareds, they cancel out. And that is very, very good, because we do not like that. Because G is long and complicated, and nobody likes fractions. So, we can rewrite this as a cubed over 1 AU cubed equals m over solar mass times p squared over 1 year squared. And this right here will give us so this tells us that if we use the units, astronomical units, solar masses, and a year in our equation, a cubed equals mp squared. But this right here only works if A is not solar masses, is astronomical units, M is solar masses, and P is 1 year. So now that we know this, let's test it out on something. Let's say Mercury. Now, using this computer over here, I have determined that Mercury's distance from the Sun is 0.39 AUs. So we'll do 0.39 AUs cubed equals 1, which is pretty simple, and then p squared. So I have this one, and this is what also makes it quite easy. Since we're using solar masses, and the Sun plus the weight of Mercury is almost exactly equal to the Sun plus the weight of Earth, and the Sun plus the weight of Earth or mass of Earth, is almost equal to the Sun plus the mass of Jupiter. A solar mass is always, we're just going to refer to it as 1, not 1.03257. No, that's just really complicated. Just 1, because, if you're using kilograms, what's the difference between 3,572 kilograms and 3,500 kilograms? Not much, especially relatively. So, we're going to say 0.39 cubed equals p squared. But what's with this? We got 0.39. I want to round that up to, 0.39. We'll go that up to 0.4. I'm not comfortable with going up to 0.5 because that might be too much. But we'll take my handy calculator here, and we will say 0.4 cubed equals 0.064. 0.064 equals p squared. Then we shall root both sides. So root 0.064 right there is, oh god, oh goodness, we've got a seemingly irrational number. 0.25298 ... is approximately equal to the orbital period. But just as we sort of rounded earlier, how about we round with this? I see this 0.25 right here. I like that. So let's cross these guys out, and we'll just say 1/4 is about equal to p. And so we now know that Mercury's orbiting period is about a quarter of a year. So let's do 365 divided by 4. 91.25 days. So yeah, 3 months, which is, every season it goes around. Okay, we did a really small planet, but just to make sure you guys get this, we're going to do a really big planet. If you think you got it, please, by all means, stop watching this. But we're going to do Saturn now. So we'll take that and put these papers somewhere special. And, okay. So, a cubed equals p squared, because we already know m is going to equal 1, so what's the point of putting it there? Okay, Saturn is 9.5 AUs, and ta-da! So, this is pretty simple, you know? 9.5? Heck, let's round it to 10. Why not? You know what? When you're out in these huge distances, you know, and to prove it to you, we'll do 9. I did 10 cubed right here. That's 1,000. 9.5 cubed is 857. So you know it's a pretty large distance. So you know what? Let's keep it at 9.5, even though I don't like it. I'm still a bit, you know, I want to stay cool. I don't want to way overshoot this, because I don't want to change the equation way too much, even though that's only 150, a difference of about 150. So, unfortunately, we're going to have to go to 857.4 equals p squared. This isn't fun. Oh well. So, 857, oh wait, gotta root that. Root 857.4 equals, whoo, 29.28. So, here we go. I mean, it's not a pretty answer, because it goes, actually, right there. Can you see that? 29.28139.341, yeah. No, we don't like that. And 28 is pretty close. So, hey, 29 years. 29 years is our answer. So, there you go. That is how you calculate the orbital period, the mass of something, the semi-major axis, and so this is, you know, it's cool if you're bored or something, you know, you can say, okay, let's look up the AU of another planet that we might have found, like, I don't know, Kepler 22b, I'm sure they have. That Earth-like planet they found last year, that's pretty cool. You could do that, or, I haven't tried this, but, you know, maybe you could find a train track around Christmas time, and you have the train track here, and you could measure you can measure from the center how long that is, and you can time how long it takes the thing to go around, and you can calculate if this train was in real life, how much it would. Of course, you have to translate this into astronomical units, which would be very, very small. So you might have to do the equations with the g's and the 4 pi squareds, but it'd be cool to see, you know, like how much, if this was a planet, how light would the star have to be in order to keep it that small? You know, just a cool little idea. But this has been the Newtonian modification of Kepler's third law, helped in a large part by Charles Balin. Thank you, Charles. I will see you next video. Bye.